Hello everyone. Today we will start with the session 3 of week 2. And this session we are talking of CUDA in containers and continuous integration validation of the programs which we write step by step every day. So by the end of this session, we are going to understand how the CUDA program actually executes. So what is the CUDA execution model? What's the difference between host and the device? What are kernels? What's grids of blocks of threads? Just in brief, not in detail. Then we'll try to compile and run a vector add kernel inside a developmental container. That's the hands-on. And we'll try to understand a three-level probe. That basically means we are trying to still understand what's a driver, what's a toolkit, what's the framework to localize the GPU stack failures. And we'll try to design a continuous integration pipeline. So we build something like the smoke test. The basic idea here is the smoke test, by name itself, indicates that we're going to test it with a very, very minimal, very fast thing, but basically means we are syntactically correct, we are executing the program correctly on the required hardware with the required framework, and it's not actually breaking down, right? Then we scan it, push it, and then try to run it on GPU aware with certain caveats if needed, right? So this is the basic idea about what we are going to learn in this session. So let's start with why are we going to touch CUDA in this course? So the basic idea here is the smallest kernel which we write for our programs in any of these deep learning applications, as well as any of these massively parallel programs, we try to write them as kernels. And these kernels basically compile and runs on the proven drivers, toolkit, and the GPUs if all of this whole pipeline agrees, right? So independent of any framework which we're using. There are logs and errors basically if generated in terms of CUDA. You will get invalid device function, SM100, illegal memory access. And basically we need to understand, we need to read them actually as to what it means. Wheels and kernels are compiled basically on a specific GPU architecture. We're talking of architectural targets. I'm not going into the details again, but this Blackwell is equal to SM underscore 100 basically means we are at the Blackwell series of GPU, which are the latest ones. So your architecture keeps on changing. I have told you a simple architecture, Blackwell. Okay, it's a streaming multiprocessor underscore 100, SM100. And then these type of mismatches generally surface as runtime errors. So what we are trying to tell is when you change the GPU architecture, right, your drivers, your wheels, okay, your toolkit, everything needs a change, okay? Or if it is continued, it has to be compatible, okay? That's what it basically means. So if you see the minimal viable mental model of how CUDA execution model works, okay, so there are two things we are talking about. We have the host, which is the CPU, and we have the device, the GPU. Now, basic idea is whatever heavy work which we intend to do in massively parallel way is supposed to be offloaded to the GPU, okay, and then the GPU does all the computationally intensive parallel processing, okay, and then returns us the result back to the CPU. So basically the CPU just allocates plus copies the data to the device, and device has a global memory which can be accessed nowadays because of the unified memory, okay, concept at both levels, right? So the basic idea is we allocate and copy the data from the host to the device, and device basically executes everything taking that data okay, and then copies the result back. So we actually launch the kernel in a sense that specific compute kernel which we are trying to run on the GPU, and GPU should always be used to run specifically the kernels, nothing else. Okay, and these kernels are specifically the functions which are run by thousands of threads at once, and each of these threads have their own index. Okay, so there are blocks, threads, and then you launch those threads on those blocks. Okay, and those blocks basically have grids. Okay, so this is how it's going to happen. And frameworks like PyTorch basically help us to do this, which basically are pre-written and tuned in case of tensor operations. So we're not going into the details again. The basic idea has to be like you have got blocks, you've got threads, okay, and then you have a grid. Okay, so let us try to understand what it means by the CUDA execution model in detail, and what's a warp, what's a thread, what's grid, and what's block. So from the thread hierarchy perspective, okay, there are at the lowest level threads. Okay, so basically a thread runs on one CUDA core, and it has got the private registers, right? A group of threads which is warp, which basically is 32 threads, and this is the basic idea of CUDA execution, that the SIMT execution, that is single instruction multiple thread execution, actually is done in groups of 32 threads. Okay, so the hardware scheduling unit or the scheduler basically schedules 32 threads as a warp. Okay, and then we actually have the streaming multiprocessor which we say, and there is a block, okay, which is up to 1024 threads, and that block basically runs on one streaming multiprocessor, and it has the shared memory type of a concept for the whole of those threads in a particular block. And then we have got a grid wherein there is one per kernel launch. So there is one grid per kernel, which we say, right? So threads in a warp execute the same instruction simultaneously. Okay, so there is this serializable block, right, which we should understand. And then basically that is what is very, very important in terms of parallel processing, that we need to have serialized blocks. Okay, so that is one thing which we should keep in mind. And then there is this way of launching the kernel, specifically the launch configuration: 1D grids of block, 256 threads each. And then that basically means that we have this way of trying to run the threads, okay, which basically are executing the kernels in a specific fashion, in a specific way, okay, specifically. And then this is how basically the GPU memory hierarchy looks like. Okay, so you have got registers, you've got shared memory space as in terms of blocks, and then there are certain things in terms of grids. So we are trying to even think about the PCI Express bus, which connects the CPU to the GPU or the host to the device, right? So that also basically is the communication medium, right, which transfers the data from the host to the device. And once the device executes everything, the result has to come to host, right? So there are basically mechanisms by which we should minimize this PCI transfers, right? And we can use something called as coalescing the global memory accesses. Okay, so these are certain things which are to be remembered when you develop these programs as we go along, right? So there is this concept in case of CUDA, and specifically the memory management aspect of it, because each GPU has got a specific memory with which it can work. Okay, so GPU as a device has a specific size of the memory with which it can work. Now, the concept of this explicit transfer from the host to the device and from the device back to the host can be traded off with some concepts which are called as concepts for unified memory, right? So there's a trade-off which talks about how CUDA malloc managed, okay, could be used for the concept which is termed as unified memory. And that basically means that there's a single pointer which is accessible from the host and the device. So that basically means the CUDA runtime migrates the pages on demand. It's very simple to write. So the basic idea here is, under the hood, if we are trying to basically do the PCI Express bus data transfer, okay, then there is this concept of page fault not occurring if, okay, it can be detected as to where that particular data is present. Okay, so this basically, the idea here is you have this concept of synchronizing the content and then using CUDA malloc. Basically, this is an example. Instead of trying to use mem copy, which basically copies the data from host to device and then basically from the device back to the host, you can use this concept of malloc managed, which basically means instead of explicitly storing everything in the device when required, you can use a single pointer which is accessible both from the GPU as well as from the CPU. Okay, and it can be present there on your host machine itself. Okay, so when do you actually use this concept of unified memory? For example, when you are trying to do very fast prototyping, right, and you are trying to teach something very fast, like I am doing now, right? And we have this vector addition, that CUDA program. And then we also have certain irregular access patterns wherein we don't know, right, what to prefetch because, okay, so CUDA 12 plus basically prefetch hints, wherein there is this concept of CUDA mem prefetch async type of operation, okay, closes much of the gap. But before CUDA 12 plus, okay, we did not have this concept of prefetch hints. So there is this concept of trying to understand, right, and trying to see certain optimizations done before we can do certain prefetching, right? So the basic idea here is that we need to keep the SMs busy always. Okay, and this is the actual essence of utilizing CUDA, okay, framework basically. And this means that we need to keep the warps, okay, which are very active, to be the maximum number of warps which we can keep them active on an SM. Okay, so whatever is the maximum number of warps what an SM can be used for, we need to actually be using all of those. So higher occupancy means more warps ready to hide the latency when one warp stalls waiting for memory. See, even though we are talking of massive parallelism, okay, and we also understand that 32 threads, okay, work at the same time, okay, but still there are situations wherein the GPU explicitly also has a very fixed size of memory wherein you can actually do the malloc operation and reserve the memory for your data to be processed, or you are using unified memory. In both the cases, there will be situations where you are waiting for the memory to give you some data. So there are two types of workloads which people generally work with, and a lot of this data processing applications, deep learning applications, and all of these are actually data intensive applications because you need to transfer a lot of data from your host to the GPU, or your GPU need to process a lot of data. Okay, so there are applications which are high performance computing applications which are compute intensive, and there are certain applications which are data intensive. So we should understand for which type of applications, right, CUDA is actually needed. So we want CUDA because it's a compute device, right? We need not waste time for memory bound applications. We need to actually see how compute bound applications are used, okay, extensively, and not keep our CUDA SMs free basically. Okay, so register usage per thread, okay, is the limit which basically these GPUs give us sometimes. Okay, so there is the shared memory per block. What can be the block size? It should be in the multiples of 32, 120, or 256 or whatever, because we will have to work with 32 threads as a group, right? So basically multiples of 32, so on and so forth. So there is this rule of thumb which talks about the block dimension. So the whole block, so maximum is 256 threads per block, right? And there are minimum 4 blocks per SM is what is the configuration which generally we launch, okay, our kernels with the configurations like this generally. Okay, and then there are these tools which are profiling tools, which are like Nsight and so on and so forth basically. So NVIDIA Nsight is a profiling tool, so we can use those tools for optimizing our runtime behavior, right? And just try to see that our SMs are always kept busy. Okay, now there is this concept of CUDA streams, which talk about how do you overlap compute and data transfer. So let's try to understand what a stream is. So stream basically is a sequence of CUDA operations that execute in an order, and multiple streams can run concurrently. So that basically means there is this sequence of operations that are supposed to be executed in a specific order, and then you have different such streams, okay, which can be run concurrently. So default stream 0 is synchronous with all other streams. So the basic idea here is the way in which we talk about the main thread in case of MPI programs, okay, or the thread number 0 in case of OpenMP programs, and then you have got multiple threads which can basically work in parallel. The same concept holds good here. So you've got a lot of streams, like you have got, let us say in this example, you have got CUDA stream S1 and S2, okay, and these are two different streams, and you run those streams in parallel on two different kernels with different blocks, okay. And then there is this concept of overlapping, wherein you are trying to transfer the next batch while computing the current one, okay, something of that sort. So you can basically do certain synchronization, and then you can actually exchange the information, and these are what three streams means. Why it matters basically, without the streams your host to the device transfer, okay, basically of the kernel, and then basically from them again the kernel execution, then device to the host transfer, basically all are sequential. It basically means the transfer mechanism, okay, is basically sequential. So because of the bus which you are using, it's all sequential. So with two streams you can overlap H2D of batch n plus 1 while kernel processes batch n. Theoretically, it is 2x throughput on data parallel workloads. PyTorch uses streams internally for this. So the basic idea here is it is something like the communication medium which you are trying to use, okay, is a sequential medium. So you'll have to transfer the data sequentially. But here, actually what you can do is you can overlap, okay, the host to the device transfer and the kernel operations and the device to host transfer back in a synchronized manner, wherein they can overlap and use the same bus, okay, for increased throughputs, right? So that's what basically it means. So there are certain areas wherein there is this silent failure problem, wherein kernel launches will never return an error code directly, okay, because they are asynchronous, and invalid memory access inside a kernel will be only visible when we are trying to do some synchronization, okay, of the CUDA function. So the basic idea here is there are certain cases wherein there are these invalid memory accesses which are basically very very important, because you are talking in terms of lot of threads, right? And trying to basically debug all of them is very very tedious job, right? And for that you require a lot of profilers, you require a lot of uh, memcheck tools, okay. So you have to basically catch out of bound things, okay, unaligned things, so on and so forth. And these memcheck things, right, when we talk about CUDA memcheck, so on and so forth, only for debugging, these basically add, okay, lot of overhead to our programs basically, okay. So what essence I'm trying to put forth because of this slide is that we need to actually understand the launch errors, and we also need to understand the async errors because we are trying to do synchronization, okay. So these are all certain problems which you will encounter when you start working, okay, and develop your applications in the other chapters as well, okay, other units as well. So how do you actually execute and build a CUDA program? So the basic idea is this NVCC compiler. So this is a modified C++ compiler by NVIDIA. So that's why you call it as NVCC compiler. And the basic idea to use this compiler is that you have to understand the whole CUDA build tool chain, right? So what I am trying to show you here is there is this pre-processing which talks about NVCC calls the C++ file. There are preprocessor statements like hash include, define, all of that. Okay, they are all resolved. Then the NVCC compilers, the first step is that your CUDA C++ program or CUDA program basically is compiled to a PTX format, okay, which basically is the parallel thread execution, okay, type of assembly level program for the GPUs, right? And then once you get the PTX intermediate, conversions file, that assembles the PTX to streaming assembler for target SM architecture. So this is where the actual essence of the NVIDIA compilation is important. So you write a CUDA C++ program, you convert it into a PTX. This PTX thing, okay, is again assembled back, okay, to the streaming assembler thing for a specific SM architecture. And then this NVCC calls the system C++ compiler or G++ compiler for the host functions. So you have the host functions, right? And you have certain device code. You have got certain codes which are specifically to be targeted for that specific SM architecture. And then you have this host object of the device linked basically into a final ELF binary. So we have got things like compile for the current GPU. These are certain commands which we'll be using. We'll use NVCC. So NVCC, the architecture is native architecture, vector program, vector edition program .cu. This is my source code. That's a CU code, the CUDA code program, objective, and then the executable, the same way in which we compile a GCC program, right? So we can generate the PTX for any architecture which we talk about. So here NVCC uses a compute underscore 80 architecture, okay, and then you use the code for SM80 and SM90, any one of them. Then you do this add.cu minus add. So this basically means that then we can inspect the PTX output using the cat command, and then we can use the make file to understand and then see how we are going to run this on which architecture with certain specific flags. Okay, we'll see all of that when we execute the programs. So I hope this is clear. So the basic idea here is to make people understand when they start working on a GPU and when they use the NVCC compiler, it has all of these steps inside. Okay, so when we are now running everything on a container, so now initially I showed you the container, I told you what it means, I told you about Docker. Okay, now what are the containers which actually support us to write CUDA programs have in them? Okay, so from the developmental point of view and from the runtime point of view, let us try to understand that what each image is going to contain and what are the various components. Okay, so when you are trying to see from the aspect of what is that the container image at runtime will have, what will it be there when you are trying to do developmental container. So see here, CUDA runtime, CUBLAS, NCCL, NVCC compiler, CUDA header, static libraries, PTAX, image size, whatever. Okay, these are the components. And if you are talking of a runtime container, it will only have two things: CUDA runtime, that is libqdart, and then CUBLAS, CUDNN, and CUSPARS. Right? These are the various libraries. And from the developmental aspect, if it's a container which is a developmental container, you will have all of this. Okay, so the basic idea here is we compile the whole thing in develop, copy that binary and run that in the runtime basically. Okay, so that's a multi-stage pattern basically where everything is generally done like. Okay, so we'll try to do this vector addition. Okay, and we have written a vector addition kernel. So please try to understand this. We are trying to use here, okay, include, then this is a global um, okay, global function which is underscore global void add, which talks about using A, B, and C. Okay, vectors. So the basic idea here is C is equal to AI plus BI. That's how a vector addition is. Okay, and the basic idea here is we are trying to use CUDA malloc manage. Okay, that basically means I am not specifically copying the content, okay, from my host to my GPU explicitly. Okay, otherwise I would have to write, okay, CUDA mem copy, okay, from device, from host to device, and then back from device to host the result. Okay, now we are using CUDA malloc manage, right? So we are using A, B, and C. So we are talking of 1 million floats here. So that's how it is. And then we basically do a addition operation. So this basically means this is how you are going to run your kernel. This is the way, okay, which talks about how do we run the kernel and what are the variables to be used inside this kernel. Okay, so this is the addition operation on 256 threads. That's what we are trying to tell. And then this is how you synchronize it, and then you do the print operation for the data. Okay, so we are trying to run this using our NVCC compiler, and expected result is this. So let's try to do the execution first and then come down to the levels of failures, if any. Okay, and then we will see basically how anything which is of very serious problem could be encountered in case we also get some errors. Okay, so let us try to basically go to our programs now and see what it means. Okay, so now I have got here this folder which is 03 CUDA programs, and I have got two programs here. Okay, so once you go to this folder of CUDA programs, there is this command which I have written here. There are two ways to run this program. One thing is you can use the same thing like Docker compose up build, and if you do this, what's going to happen? Let us see. This folder has got two programs: bandwidth test.cu and then vector add.cu. Okay, so let us try to see these two programs first. So vector add.cu is basically treated as the hello world of CUDA programming. It's going to demonstrate host, that is the CPU versus device GPU memory allocation, explicit host device and device to host memory keys. This means that we're using host to device and device to host memory copies explicitly, right? But in the example, I have shown you wherein we're using the unified memory. Intentionally, I have done that because you should understand the difference. Okay? Because of the time constraint, I'm only showing you this example, but I've shown you that example also, wherein you are using CUDA memory managed, right? Which is unified memory. Now here, then you're going to do a kernel launch with a grid of blocks of threads and then some basic error checking if needed. Okay. So this is inside, we are building this as container, which is inside a CUDA enabled container or a developmental box or sandbox or whatever you talk about. We are talking of SM70, the architecture, the streaming multiprocessor underscore 70. I want you to basically understand this architecture SM/70, what it means as the assignment to this session. Okay. And if that is not very clear, please send me a message. In that interactive session when I'm conducting, I would basically be answering this. Okay. Or any other question also if you have. Okay. So this is how it is. And the result is it will tell us which GPU we are using and it's running on which specific NVIDIA GPU. It's computing C is equal to A plus B for N is equal to these many elements. You can change the elements also and how much kernel time is being used and the verification has passed. Okay. So this is basically the program. If you see here, in this case, we are allocating here, okay? Allocate device buffers, put a mem copy, that means copying the data from the host to the device. So you're trying to add, right, two arrays, AI and BI. And each of them has got so many elements which we discussed, right? Again, so for the time being, to understand, okay, this is my size of the array. We can work with so many elements basically, okay? So this is how it is. We are trying to allocate the buffers, host buffers with certain specific data, right? And the data is the static data, okay? So this is how the data to the into the static, whatever value we are trying to put in A of 1, A of 0, A of 1, A of 2, A of 3, and then B of that. We are actually multiplying that value with 2 and then trying to put it in the array B. So this is how we're going to actually allocate the buffer in our device, because I know that there are so many elements I'm using So that much amount of elements I need to save the space for in my GPU as well, right? And then I copy. And then I configure 250 zip threads per block. And this is the general common spot which we use. And then how much time it requires. And then I basically run this kernel, okay, with so many threads per block and so many blocks, okay, and I get the sanity check if needed, and then verification, and then I need to clean up the device memory, okay. So I'm trying to do CUDA free the device, okay, for array A, for array B, for array C, okay. So this is how this program is. And now, once you use this Docker compose up minus minus build, so once I come here to the build and I build it, what effectively happens is it does everything. My Docker container actually is built, created, everything happens. Okay. And my program actually runs. Both the programs run actually. Okay. One is this program of adding elements. Okay. And then this bandwidth test, which talks about trying to understand, okay, how much bandwidth that particular specific GPU has got. Okay. So this is again the same thing we talk about on the same thing, CUDA and copies from here to there to here back. Okay. And so on and so forth. So the basic idea really is again the same. Okay. So it's basically talking about trying to understand, okay, the device memory bandwidth via copy kernel. So we are trying to do the sanity and okay, all of that. You can just go to the program and then now one of the things is let us try to see our container is run, everything is run. But what effectively happens is how do I actually do the NVCC thing, the compiler thing, everything, right? Now here what I did was I have built everything. I have composed that my Docker file has got all the things which I need to do. Okay. So what I have tried to do is this particular Docker file, which is there. Sorry, this Docker file, which is there. Okay. Here basically talks of again using this and it compiles all my programs which are there in that particular folder. Okay. Now vector add thing, okay, and the band thing. And then it runs both of those programs and then gives everything up, doing everything. Okay. Now in case I need to actually do some interactive debugging inside the container with CUDA programming, right? Well, how do I do it? So for that, there is this particular thing which talks about we are going to run a Docker with this IT, okay, this command which is minus IT switch, okay, and a path, okay, and the two programs are there now in local and then bash. So what effectively it happens is I get an interactive terminal inside my container, okay, and I work at the root prompt of my container with Ubuntu installed on it, right? That is what we did for a Jupyter developmental notebook, right? So let me try to execute this command and then see what actually happens. See, I am now inside the container, okay, and I'm at root prompt. We'll just try to understand what all this has. Now, see, I'm able to interactively see all of my programs, okay? And let me now just check NVCC minus version. So which of the NVCC compiler, okay, or NVIDIA compiler I'm using for compiling everything inside my container. See, it tells me that I'm using CUDA compiler. It's a specific driver, okay, and it's a tool, it's 13.0, okay, which I'm using. Now here, I can run my programs, which are this vector add.cu, okay, and bandwidth test.cu. So if you want to run these programs, okay, I have compiled it. We can compile it, right? The same command nvcc -o, okay, and the file name .cu -o and the file name. And I have compiled it now. So similarly, you have to execute it. Let us say I want to execute this now. Vector underscore add. Okay. See. So it means my program is running on RTX 3050. Okay. It's SM 8.6. Computing is equal to A plus B. But these many elements, but I have kept it to be just 20. And it takes so much time. You can add the numbers, you can change the numbers, you can do so many things. And similarly, if I want to run, let me just show you the way in which it can be compiled. NVCC, right? You go to the EPP, right? So the way in which it has to be compiled is something like NVCC. Okay. I will just use a shortcut method, vector underscore add dot c -o. I'll see VA now. Okay. Instead of vector underscore add as the executable, I'm just trying to see VA, and let us try to see what happens. I try to see this, and I get the VA as executable. So now I can run. Okay. See. So that's how you compile your CUDA program, right? And if you want to see it at this level, let us see if I have this. And similarly, if I want to run, let me just show you the way in which it can be compiled. NVCC, right? You go to the EPP, right? So the way in which it has to be compiled is something like NVCC. Okay. I will just use a shortcut method, vector underscore add dot c -o. I'll see VA now. Okay. Instead of vector underscore add as the executable, I'm just trying to see VA, and let us try to see what happens. I try to see this, and I get the VA as executable. So now I can run. Okay. See. So that's how you compile your CUDA program, right? And if you want to see it at this level, let us see if I have this nano here with me. Oh, nano is not there, so we'll have to use something like VI. Okay. So we can use VI and see a program here. Okay. So we can edit, we can do at this prompt itself. Okay. So anything. Let's see if we'll do that. So VI else is not there. So in case you have to do, you have to actually install inside the container editor like VI or Nano, right? Or whatever. Okay. So this is how actually it's going to happen because of the way in which we have installed and what to say, compiled the various things inside our container basically. Okay. So this is how actually it's going to work out. So I can exit now. Okay. And I have exited out of my container, and we have interactively worked inside this container for our program. Okay? And that's a specific CUDA program. Okay. Now there is another this smoke test.py program which you can run. Okay. And I will basically try to show you on certain things of how you're going to run it if needed. Okay. Otherwise, you can basically try to see what it does. Okay. And run it and then see basically how we are going to use it. So there are 2 or 3 things that we did today. We entered into the container, tried to use NVCC basically. Okay. At that level of compilation, we compiled our own CUDA program. Okay. And then ran it at the command prompt inside a container. So our CUDA program got executed because we have installed the CUDA driver. It can access the GPU. Okay. And there is this bridge between the CUDA driver, okay, and the GPU okay, and the actual CUDA toolkit. Okay, so all of that are all synced now, or okay, and they are actually compatible to each other, right? So, okay, I can show you the NVIDIA SMI also. Let us see. So now, where will this NVIDIA SMI basically be found out? Okay, so if you run interactively, okay, and we enter into this, there is where, okay, if you see this NVIDIA SMI command, it tells us as to what particular GPU we are working on. So this is basically a RTX 3050 GPU, right? It's a laptop which has got a RTX GPU, right? So the intention I am using a laptop is to make sure that you people can use your own laptops as well for trying to execute these programs, and you can access any clusters which you have. Okay, in one or two examples as we go along, I am going to connect to DGX H100 server, okay, as well as DGX 300 server, and then try to do certain programs which will be run on those servers as well. So it's almost the same. So the intention is majority of the people can utilize all of these programs on their own independent GPU laptops. Okay, so this is how you can basically start working on your own GPU programs. Okay, so I told you about the NVIDIA SMI. So there is this problem of the mismatch between the driver. Okay, there is the mismatch between the driver, okay, and then the container and the GPU not being visible. Okay, then at the toolkit level, we can actually see whether the CUDA code compiles or executes. We have done that. I compiled it and I showed you. The framework level, basically I showed you in the initial program itself that we can import torch and try to see torch.cuda is available or not. So whichever level fails first names the layer to the fix. That basically means whichever level fails first names the layer to fix. That basically means at whatever level we are failing, that basic layer or level needs to be fixed first. So never debug level 3 before levels 1 and 2 pass. That basically means that we cannot work at the framework level and try debugging that in our programs in future when my driver, SMI, toolkit, all are not compatible. So it's never going to execute. Please understand this. This mistake is oftenly done and people get frustrated because of the mismatch in the toolkit, the drivers. Once for all, if you sit patiently and do and set up your driver, toolkit, okay, and the other things for your system once, then it will become very easy for you to work and you'll start enjoying actually the way in which the GPUs actually execute programs. Okay, so now whenever we are going to do this commit, okay, for our own continuous integration pipeline, our tags, the updation need to be actually updated because environments rot quietly in a sense that if we don't put a correct tag, right, our wheel will break. Okay, and that's very, very frustrating because you'll not be able to maintain the versions. You will not be able to actually see any updates correctly, and there will be chaos. So we need to understand how do we actually do commit with a specific way of documentation or basically tagging, right? And every commit step by step which we do, we should test it, see that it works, and then go on iteratively improving. So that's why the name continuous integration. Okay. And that is very, very important. Most hosted runners are CPU only. Smoke test must degrade gracefully. That means import plus CPU operations with full GPU tests on self-hosted runners. So that basically means when a lot of these frameworks or libraries you start using on GPUs silently, right? If GPU is not available, they will shift towards the CPU operations and complete the task. So one of the things which we should understand is that we have to specifically install the libraries, the packages, which are specifically meant to be running on GPUs. Okay. So this is what it means. So these are certain things which we should keep in mind. And always remember there will be 4 stages. I have not gone into the way in which you work with the repository at present, but gradually when we try to develop a specific Docker application, push it to the GitHub, then build it iteratively over a long time, and then try to actually use it for building our Docker container. Okay. We would require that. But for the time being, we need to use build, run the image, basically, then any imports needed, versions. Okay, all of this very, very fast we should be able to do the smoke test. And then we do scanning. That basically means if we are trying to do certain boundary condition type of stuff and we are supposed to be doing testing things, we need basically to understand that very, very critical findings we need. Are we failing, right? All of that. And then we push. Okay. So push only after 1 to 3 passes. So this means basically we need to build very fast. The registry cache needs to be understood, or it needs to be very, very valid information there in the cache. And then we need to do a very, very fast smoke test and check on the scan with boundary conditions, so on and so forth, and then try to push. Okay. So there are certain cases wherein, as I told you, right, runs in CI, CPU, and on GPU, right? So basically, the idea is to do certain import, then print torch, as I told you, right? So if the torch.CUDA is available, it's hosted. Otherwise, it will tell GPU is okay, you get the device. Otherwise, CPU only run and GPU checks skip sometimes. So this basically means missing libraries, we get broken wheels sometimes, there's a version mismatch. Okay. And then all of these things are there wherein we have CUDA-less wheels. Okay. So there is this concept of true tire wherein wherever GPU assertions are there, the hardware exists, we assert, and if not, then CPU assertions everywhere, right? So this is the way by which we can actually try to work inside the container, okay, and then try to see things, okay. So this is what I thought I'll cover in session 3 today, okay, and we will see certain other things and complete the 4th and the last session of this week, okay, in our next class. Thank you.